Aubin, who's giving the SOCAAR Seminar today. Dan got his undergraduate degree at York University in chemistry, worked with Rob McLaren, I believe, and then came down to UT in chemistry, got his PhD with me, graduated about 10 years ago, a little bit over 10 years ago. He worked on studies, sort of basic physical chemistry studies of the interactions of small gases with soot surfaces. So we looked at like nitric acid, NO2, small aromatics, small AHs on soot, and did the kinetics and the sort of thermodynamics of those interactions. And then he left Toronto, moved to Ottawa to the NRC, National Research Council, and moved into more applied work in the indoor air quality team there. And he's recently become the team leader of that effort. But you might hear more about it today. But I was talking to him last night about it. So it's a large effort, a couple of $1 million a year, 15 people in the team. And so I think he's going to be talking about some of those projects today. So I'd just like to welcome him to speak.
No, let me just put it away so that we have
Okay, well, thank you. So yeah, garages, pollutants, reducing exposures, that's basically the crux of it. So this was a joint study. NRC collaborates very closely with Health Canada on a number of indoor air quality issues and human exposures. So the study was motivated by some of our collective previous work that had shown that if you have a garage, you essentially get exposures to elevated pollutants that are not very good for you. So the majority of Canadian homes have a garage, and these garages in winter tend to be at a lower pressure, or these garages tend to be at a higher pressure than the home. So what happens is that you essentially draw in polluted air from the garage into the home, along with anything else that's in there. So that is an issue if you've got a garage and you've got a bunch of sources that are emitting potentially dangerous things like benzene, which is a carcinogen. You can and will end up drawing that into the home. And then in some cases, in cold climate environments, they saw that you can get significant intrusions of carbon monoxide into the home, and that's just from starting the car, taking it out of the garage, or putting it back in. So it's not like somebody's in here running a vehicle for an extended period of time. And some of the previous work from Don Fugler shown that a significant portion of the actual whole air volume of air in the home can originate from the garage, almost up to 50%. And along with that are these harmful pollutants. For example, indoor CO can be up to 60% coming from the garage. Again, that's another Canadian study. And an important one too is benzene, particularly VTEX. Benzene's a known carcinogen, and the guidelines are reduce your exposures to as little as possible. So it gives you an idea of up to the point you want to reduce benzene. And up to 50% of the total benzene in the home can come from the garage. And that's irrespective of how you're using the garage. So if you're not using it to park your vehicle, but you're storing things like lawnmowers, snowblowers, small combustion engines, or storing on whatever you have in your home, paints, this or that, that will affect your indoor air quality. And so what drives that? Well, I said that there's a number of different mechanisms. That's basically that the home is depressurized relative to the garage. So obviously if there's a poor air barrier between the home and the garage, or you're going in and out of the garage from the home, you are going to be essentially drawing in air from the garage into the home. And there's a few mechanisms that contribute to that. One of them is just wind-induced airflow. So just on a windy day, you will draw in air into the home. Also, if you're using mechanical ventilation systems and they're not balanced, so example, if you have some homes only have an exhaust ventilation system, so your range hood or your bathroom, that's the only mechanical ventilation you have in the home. So if you're running that continuously, you're essentially depressurizing the home. So that's another contributing factor. But the most important one is in winter, and that's what's called a stack effect. Essentially, it's like a chimney effect. You've got cold air infiltrating at the lower portion of the home, and then it's rising in and exfiltrating out. So that drives most of the air exchange rate and airflow in winter. And that's the period that we were concerned about specifically. Again, back to some of the previous work that was done on this issue. So we were aware from other studies that this is common in Canada. So what we have here is, this is for a study that was done by Health Canada in Windsor and Regina. These are the benzene concentrations, and you can see that if you have an attached garage, you have significantly higher concentrations of benzene in the home. And this is a study I did in Quebec City, and again, we see the same thing. So, and this is regardless of what you're doing with your garage. So just having a garage that's attached to your home will lead to higher concentrations in the home. So before we started on this study, we wanted to get an idea of what historically were the prescriptions for, how's a garage supposed to be built? How do you ventilate it? And what do you do with respect to the building code? So we historically we went over through all the different editions of the National Building Code, and what we see is that sure, the definition of garage has changed over time, but it's essentially what we see are commonly are these three types of garages. So you can have an attached garage and a detached bungalow, which is fairly common. An integrated garage, which is basically what you would see in a townhouse. It's basically set into the home. Or you can have, in some cases, you'll have a garage that leads into the basement. So this is what you could expect to see in the field. But the National Building Code doesn't say that you need to ventilate your garage unless you have more than 5 vehicles, or 5 or more vehicles in the garage. So there was really nothing specific about how to reduce pollutant concentrations, even though everybody would expect that you're parking a dirty vehicle, there's going to be stuff coming off of it. So regardless of how many vehicles are parked, if you have a basement garage, there needs to be a fairly good fire barrier, and that's obvious because a lot of these basement garages will have a living space above them, so if there's a bedroom there, that's the issue. And the other attached and integrated garages, well, you don't need a fire barrier, but you do need to make sure that the garage is airtight as much as you can. And that's about as specific as they get. Try to maximize the airtightness, which really doesn't give you much to go on. And some specific prescriptions, well, if you have a garage, you want it to be airtight, so you're going to have to put some sort of membrane in between the garage and the home. And that you see that like the Tyvek sheeting on when you're building a new subdevelopment. And if typically you'll have a door leading from the garage into the home. We didn't see a home that didn't have that. That's so basically all the cases. So if you have that, you want to make sure that the door is properly weather stripped, basically gasketing to make sure that it's airtight as much as it can be. And you want to make sure that there's the door closes automatically. So most people here, if you've been in a home with a garage door that leads into the garage, you'll see that usually it's a lot harder to open and close, and it closes automatically. And that's to make sure that the door doesn't stay open for an extended period of time. And then obviously you don't want this leading into a bedroom, so you didn't see anything like that. Typically your garage door, once you get into the home, it will lead into some sort of a hallway or a mudroom or what have you. And if you're going to use a membrane, you have to make sure that it's properly sealed and everything. So that's basically all the prescriptions. And we were looking at developing intervention techniques that could kind of improve on this to reduce the air transfer. So we did a survey at the Canadian Home Builders Association probably 4 years ago, and we asked them, what are your construction designs for detached homes with garages? And this is what they came back to us. Mostly integrated, mostly attached, and some of them are integrated. And what we saw in our study in Ottawa, which had 36 homes participating, is we roughly saw the same proportions. Most of the garages were attached, and then the rest were kind of like townhouses. So the experimental design was fairly straightforward. It was an intervention field study. So what that means is you need to monitor the exposure to pollutants in the home both before and after your intervention. So it's a combination of a regular exposure study, which most people are probably familiar with an intervention, and then you're testing the effectiveness of that intervention. So the first intervention we looked at was fairly simple. And some of the literature suggested this. Well, what if you added a continuously running exhaust fan in the garage and have that running? You're going to depressurize the garage, and you're also going to exhaust the polluted air in the garage, and that you would think would reduce pollutant concentrations in the home. And the second intervention we looked at was the improved sealing of the common wall between the garage and the home. So going in there, hiring some weatherization contractors to go in there and improve that seal. And so this was done over 2 years. First year we did the exhaust fan intervention, and then we came back the second year, deactivated the garage exhaust fan, sealed it up, and then did the sealing intervention and then carried on. So that's what I'll talk about today, the two aspects of this study, both the exhaust fan and the sealing. So on the ground, this is what it looked like in the field. So because you're concerned about human exposures, you're obviously going to be looking at environmental pollutants, which is fairly straightforward. And you're also dealing with the building science side of things, so you need to know things like ventilation rates in the home, interzonal flows between the garage and the home, the air tightness of the building envelope, and then we also did a number of questionnaires and time activity logs to get a better idea of how they're using your garage, what are they storing in it. So we did an inventory of the garage. And then we measured a number of compounds like volatile organic compounds, carbons, total volatile organic compounds, aldehydes, and then the rest of the usual things you see: CO, CO2, humidity, temperature, NO2. In this case, for the exhaust fan intervention, we looked at the pressure differential between the house and the garage. So how does that change when you start running the fan? Because that was the main crux of the exhaust fan intervention. Was they looked at the literature dealing with asbestos, and they looked at asbestos clean rooms and what were the protocols for that. And to safely work in that environment, you needed a delta P of 5 pascals between the lab itself and anything outside to basically make sure that there was no driving force or air contaminated with asbestos to leave the lab. So we thought, well, maybe you do the same thing with a garage and that'll be good enough. So to do that, we obviously wanted to measure the delta P of between the house and the garage, and also between the garage and the exterior. And we also added some sensors in the doors, the main garage door and then the door leading into the garage to see how it was being used. And then we measured all these parameters in the home and the garage. And on the outside and basically in the backyard, we measured VOCs and NO2 just to be able to correct the background concentrations. Likewise, for the second intervention, for the sealing, we did reduce the number of parameters we looked at. We figured out that those door sensors weren't really working properly, so we stopped using them in this phase of the study. And again, we looked at all these measures. And it was really important to look at the building science side of things and the sealing intervention, because we wanted to characterize how effective was the weatherization at improving the tightness of that wall. And we also wanted to see how the interzonal flows between the house and the garage were impacted. So just to get into analytical methods fairly quickly here. So for the VOCs, we looked at both active and passive sampling. So what I have here are these SOCAAR canisters. Those were deployed in all 3 locations, and we had those analyzed by Environment Canada. We also did some passive sampling with these basically passive sampling thermal desorption tubes. If you're familiar with analytical chemistry, they're about this size, and you basically take the caps off, leave them in the home for a prescribed period of time, and then bring it back to the lab and analyze it by thermally desorbing whatever's on the tube and then analyzing that with the GCMS. And that's what that passive sampling tube looks like. We also wanted to characterize the ventilation rate in the home. And to do that, you need to use some sort of a tracer gas technique. So you know how much tracer gas you're emitting in the home, you measure concentration as a function of time, and then from that you can back out what the air changes per hour is. And we used an existing method provided by the down in the States by Brookhaven National Laboratory. So basically you have a little aluminum plug full of a fluorinated tracer and basically a silicone plug, and it diffuses out of that cap, and then you basically just stick it onto the wall, and then take your corresponding passive sampler and stick it somewhere else, and then after 7 days, or in this case it was 4 days, we would have it analyzed. Standard TVOC sensors. The NO2 is analyzed by using these impregnated Ogawa badges, and that was done at the Dalhousie University. And the air tightness, or basically what's called the air change rate at 50 pascals, was done. It's a standard method, and most of you might have seen it if you have somebody that comes to your home to see, assess the energy efficiency of your home. They will do that. Basically, they install this door into your front door, and there's a large fan, and they run the fan at a function of different flow rates and see what the pressure difference is outside and inside. And then from that, you can back out a air tightness. And the term for that is the air changes per hour at 50 pascals. And then all these other sensors here that I had mentioned, and the CO, temperature, RH, and the sensors. So some of the, I want to give a bit of background here. When we're talking about ventilation rates, it's more than just the, I did mention the air changes per hour, but there's more than just that. So what the air change rate is basically the amount of time it takes to completely exchange the volume of air in a space. And that's usually air changes per hour, given right here. And that's a function of the amount of the volume of air that's infiltrating in the home. So if you've got a really leaky building envelope, you're going to get a lot of stuff coming in the home, both in and out. And that's driven principally by the temperature difference, as I mentioned before. And then you also have things like mechanical ventilation. You can be bringing outside air into the home. And then you also have something called natural ventilation, which is just basically opening and closing doors and windows. So that will give you the overall air changes, the overall air change rate. And then you could either do an integrated measure or an instantaneous measure. We integrated it over a 4-day period. And then along with that, we wanted to figure out what the flow of air between the different zones was, because you want to characterize how much air is coming from the garage into the home. And if you have multiple tracer gases, you can do that. You put one type of gas in the home, one type of gas in the garage, and a sampler in the garage, and a sampler in the home. By solving this rather trivial algebra, you can back out an interzone flow in cubic meters per hour, and that's what we did in this case. So the two zones that we looked at were obviously the home and the garage. And coming back to the air tightness, or the air changes at 50 pascal, basically when you run the fan here at a bunch of different pressures or depressurizations, you get what's called a leakage curve. And then that gives you information about the air tightness of the home. So just some of the housing characteristics for the participating homes. So most of them were, as I mentioned, single-family homes, detached. And most of them, they only had one common wall, which made it pretty easy. If you go into like a really high-end home, you might get a lot of complicated geometries with the garage. Sometimes it's really hard to tell if that section of the wall is outside, or if it's going into the attic, or if it's going into a living space. So they were fairly simple in that sense, fairly recent, again, 1960s onwards. And back to this question of a second door leading to the outside, because that's another leakage point. So that what it means here is that half the homes had a second door to exit the garage from the garage itself, besides having to go into the home and walk out. So most of the homes had some forced air mechanical ventilation system, which ensured reasonable ventilation in the home. Most of the participants actually used their garages for storing their vehicles. That's not always the case. So this is the paper that was published in 2017 on the first part of the intervention study, which was the exhaust fan intervention. So that's already out in indoor air. So in that case, what we did is we said, well, how are we going to get a delta P of 5 pascals? Well, you put in a appropriately sized fan. You set from the air leakage curve, you can kind of figure out and say, well, so for 5 pascals, I need a corresponding CFM of, let's say, 150. So that's how you adjust the fan flow rate of the exhaust fan so that you try to target your 5 pascals. And that's a fairly straightforward way of doing it. So this is the kind of, if you want to look at the broad range of air tightness characteristics. So this is the frequency count, so basically the number of homes with air tightness within this band right here. And you can see that it's fairly broad. Although a lot of homes do tend to have airtight garages. And these were the flow rates, the corresponding flow rates we needed the exhaust fan to provide. So if you're not familiar with residential ventilation equipment, you know, 2, 4, 600 CFM fans that are extremely large, and that's not something you can typically put in even in a range hood. So in that sense, it's a bit of a artificial factor, but we limited ourselves to 600 CFM. So we didn't add a fan bigger than 600 CFM, and if that's what was needed from the air leakage curve, then we just left it at that because that's unreasonable. It's like putting a jet engine into this garage and then having it run continuously while we're there. So this is what we saw in the field. So we kind of had 3 different cases. So this is a delta P between the garage and the outdoors as a function of time. So you can see that, yeah, in most cases it's negative. And then if you turn the fan on, as you'd expect, you see the delta P increase, and then you kind of get close to what we were expecting, which was good in that sense. The other case is where we, for whatever reason, the fan was running too high, or there was some sort of occupant characteristic that was impacting the exhaust fan flow rate, and we have oversized depressurization of the garage, which is not something you really want. And even a delta P of 5 is fairly large. And then in some cases, we don't know what was going on. You turn the fan on and things are all over the place, and that's typical. Homes aren't unique. You'll see all kinds of stuff. You know, homeowners go in there and do some changes, and there's different quality construction practices. So we couldn't systematically achieve the depressurization we wanted because the air tightness varies too much. So what that means is that any change in concentration that we see is likely a combination of depressurizing the garage and then just ventilating it. Ventilating continuously, you're bringing in air, so you're essentially diluting what's in the garage. So in and of itself, not being able to reach delta P of 5 is not what you get in the world. So this is what we saw. So what you have here is the indoor concentration before and after running the fan. Likewise for the garage, and this is outdoors. And you can see here fairly clearly for benzene, you run the fan and the concentration in the garage reduces quite a bit, and then you get a corresponding reduction, although always a bit smaller in the home. NO2, we see no change in the home, although we do see a large increase in NO2 when you're running the fan, but that's just because you're bringing in outside air into the garage and there's NO2 in there. So that's not surprising. And likewise for CO, we see a large reduction in the garage and then a small reduction in the home. And with the air changes per hour, we see obviously if you're running an exhaust fan in the garage, you're going to increase your air exchange rate, which is not surprising. And that's fairly large. It's almost a factor of 3 increase. So this is the, I guess, the overall impact of the intervention here. So you have indoor concentrations, garage concentrations. These are the geometric means, fan off, fan on, and the percent changed. And if it's in bold, it means it's a statistically significant change. So for what we were interested in, we see, wow, what do you know? You run the fan, you get large 80% to 60% reduction in the pollutants we were interested in that are relevant for garages. And obviously there's other things that get impacted there, like NO2, which wasn't an issue because it wasn't being changed in the home. And again, as I mentioned, you get a large reduction in the garage. So this is what this is basically showing you here is that same plot, but we segregated the homes with the garage according to how leaky or tight it was. So roughly 3 different categories: leaky, somewhat leaky, and tight. It's a not too scientific way, but that's how we kind of characterize it. And what's interesting here is that the more airtight the garage, the more pollutants are in it, which is not surprising. When you see it, it seems to be the case, and that's going to be the case for the home. And as you'd expect, again, I said for a given reduction in the garage, you'll see a smaller reduction. Basically, and then again, too, the exhaust fan is most effective in an airtight garage. So that might give you an idea of, for somebody who's already got a new home, they get it, somebody tests the airtightness and say, well, it's super leaky, then maybe you don't need to worry about this issue. And so some of the statistical modeling here. So I'm not going to go too detailed into the background, but these were some of the variables that impacted the model for statistical analysis. So VTEX, carbon monoxide, NO2, and the air exchange rate, and location, indoors or garage. See here is that, yeah, if you, the total amount of time you spend your car or you leave your car parked in the garage doesn't impact the indoor concentrations, not surprising. The amount of times that you move in and out of your garage has an effect, not surprising. But interesting for NO2, if you have a gas stove, you have higher concentrations indoors, that's not surprising. And another thing that drives the delta P or the delta P in the garage and the home is the absolute difference in indoor and outdoor temperature. So the colder it is in winter, the more air you're drawing in from the garage into the home. So now I'm going to go into the ceiling intervention. So this was presented at Indoor Air this summer in Philadelphia. This gives an overview of the result we had from the ceiling intervention. So the way that was conducted is we hired 2 weatherization contractors in Ottawa. We said, this is what we want you to do, go into the home, identify the leakage points, and seal up that garage. Again, we measured the air tightness, the flows, and the ceiling. It was pretty easy to identify the leaks in winter with an IR camera. You're depressurizing the garage, you bring in cold air. So with your IR camera, you can quickly go around and find your leakage points. And for the ceiling materials, because we were worried about VOCs, we did some headspace analysis and we did a pilot test to see that if we were going to be using these products, where we're going to contaminate the garage with VOCs in those products and then that coming into the home. That wasn't the case. And then again, all the work was done in the dead of winter, so it was about -30 in Ottawa when we were doing this. And that impacts the type of product you can use. Some of the products don't cure at those low temperatures.
We ask people online to mute your microphone. Thank you.
So I'm not going to go into too much detail here, but this basically shows you how the blower door was used in a variety of different configurations to back out an air tightness for that common house garage interface. So in the first case, where there's no secondary door leading from the garage to the outside, these are the configurations we used: blower door in the principal home, in the garage, and then the home and the garage together. And when you calculate that, you can back out, if you look at it mathematically, you can back out the equivalent leakage area for this wall here. So what we found was that you didn't need a whole lot of material to seal up a garage, basically less than a tube of caulking, half a can of expansion foam, and in all the homes we changed the weather stripping, just because some of them were fairly old. Moderate cost and time. If you hired a contractor at home, a $500 job for two individuals in one day is fairly inexpensive. What took the most amount of time was just moving the stuff along that wall so the contractors can get to it. That took a lot of time. And doing the pre and post sealing blower door test took a lot of time. But it is completely feasible intervention that any trained contractor can do. And then the common leakage points were, obviously the weather stripping is old and torn and broken up. The garage door frame is not properly caulked. That happens. You get a gap between the drywall and the foundation of the home and the electrical outlets and things like that. So this is the impact of the ceiling intervention on the air exchange rate at 50 pascals. So that's determined with the blower door. For the home, garage, and home and the garage pre and post. These are the values here at the table. What's really important here is just to look at the median. And if it's bold, it means there's a statistically significant difference. So across the board, it was very successful at improving the air tightness of the garage and a bit with the home, which was good to see. And this is probably the most important slide for this part of the intervention. This is the interzonal flows that we measured with those two different tracer gases. So this is the amount of volume flow per hour from the garage into the home. So that really gives you an idea of how much air is moving into the home. And again, we see very large, almost a 50% reduction in the amount of air going into the garage into the home. So this conclusively shows that this intervention is effective. And this is just another summary plot here. Some of the other factors, so the interzonal flow is reduced by almost half. The air tightness of the garage and homes all improved moderately. However, the VOC analysis that we did was only done in a subset of 12 homes just for scheduling issues, and with the 12 homes, we don't have the statistical sample size to show a statistically significant reduction. Although there was large reductions, it wasn't statistically significant. So for conclusion, so if you're going to look at these two approaches, the exhaust fan is very effective. You get large reductions in the garage and in the home. And it's practical. You can do it in one day. It's not that difficult. You're using commonly available construction practices and materials. Costs a little more, and the level of effort's a bit higher. And it's useful for newer old homes. However, it is an active method. You're running this exhaust fan, so there's concerns about electricity usage. And we had some anecdotal complaints about, oh, that common wall is colder in winter now that you're bringing in all this cold air into my garage, or I hear a whistling in my garage from the air fan, or from the exhaust fan. So there was some complaints on that side. For the ceiling intervention, again, we had large reductions in the air interzonal flows, and it's practical. It costs less than the exhaust fan, and the important thing is it's a passive technique, so you don't have to worry about all these issues of noise, electricity, and wear on the fan. So that's the end of the presentation here. Just some of the things that we might revisit in the future is looking at alternative ways of maybe modulating the exhaust fan use so you don't have to run it 24/7 for all of winter, which a lot of people might balk at. You know, we have all the field validated results, so we can easily do some modeling and see it. Maybe if you just run it 10 minutes an hour, or run it 5 minutes after you open and close the garage. So we're going to go back and look at things like that. So that was basically an overview of what we did for 2 winters in Aubin, pros doing field work in the dead of winter. So it was a very interesting intervention for human existing homes. And without taking any questions.